Welcome back to Z-Tech Advisor. In this module, we delve into routers, essential components in networking. Unlike switches, which function at OSI Layer 2, routers operate at Layer 3. Within our networks, routers play a pivotal role in making routing decisions, utilizing IP addresses for navigation. They rely on routing tables to determine the optimal path for network traffic based on destination IP addresses. By leveraging Layer 3 IP addresses, routers ascertain the destination network of a host and guide traffic across the wide area network to its intended destination. Once the traffic arrives at its destination network or the final router in the process, that router initiates an ARP broadcast to pinpoint the correct host on the local area network. It then forwards the traffic to the host using its MAC address, a Layer 2 identifier utilized by switches within the local area network. Over time, setting up routing has become notably simpler. In the early stages, routes were manually configured on each device. However, with the expansion and complexity of networks, dynamic routing protocols emerged, facilitating the automatic updating of routing tables for efficient traffic routing. Unfortunately, attackers exploit this dynamic nature by inserting new routers into the system to capture routing data. To counteract such reconnaissance, manufacturers integrate authentication mechanisms into router information exchanges. To enhance security, routers can be configured to implement authentication mechanisms such as single-factor authentication, which involves a password exchange before data transfer, or hash-based authentication keys like MD5 or SHA-1 hash. Employing a hash-based authentication key alongside a hash of the router information pre- and post-transfer ensures data integrity during transmission, considered a best practice for secure exchanges. During configuration, both routers manually utilize the hash-based algorithm or password as a shared secret or symmetric key. Additionally, routers serve as vital security components by employing access control lists, ACLs, on their interfaces. ACLs act as ordered rule sets, permitting or denying traffic based on specific characteristics, such as source/destination IP addresses or port numbers associated with applications or services. Actions within the ACL are executed sequentially from top to bottom, following a top-down approach. When traffic reaches an interface on a router and there's an ACL on it, it's going to perform a check of that traffic against the ACL line by line. Now, first it's going to go against the first rule in the ACL at the top, and if it matches the conditions for the action to be performed for that rule, that action will be performed, and then no other part of the ACL will be checked because it's going to stop there. Now, if it wasn't there on the first rule, it's going to go down to the second rule and then the third and the fourth, and it'll keep, or gets way down the list. For this reason, we want to make sure our most specific rules are placed at the top of the list. And the more generic rules are placed at the bottom of the list in order to secure our routers and our network. We also want to ensure that authentication is used between the routers whenever they start updating their routing tables, like we talked about using the hash-based authentications. Also, the management of the router should be conducted using strong authentication and complex passwords. Finally, our management connection to a router should always be performed over SSH, which is encrypted, and never using Telnet, which is sent in plain text over the network. As you know, network architectures are ever evolving, not only in terms of the devices that are being used to run our networks, but also the Internet protocol addressing technologies themselves. For decades, we used IPv4 or Internet Protocol version 4, and this has dominated our networks. But IPv6 or Internet Protocol version 6 has finally started to take root in many organizational networks. There are several different technologies that can help aid us during the transition period going from IPv4 to IPv6 that you may run across out in the field. This includes things that allow us to do both versions at once, such as 6 to 4, Teredo, dual stack, and GRE tunnels. 6 to 4 is a transitional technology that provides the ability for IPv6 packets to be transmitted over a standard IPv4 network without the need to create explicit tunnels. This provides IPv6 sites with the ability to communicate with other native IPv6 domains over real-life routers, and effectively it's going to treat the entire internet, which is based on IPv4, as a unicast point-to-point link layer endpoint. Now Teredo is going to provide full IPv6 connectivity for hosts, even if they don't have a connection to a native IPv6 network. Instead, Teredo is going to use a form of network address translation to encapsulate the IPv6 datagrams within our IPv4 user datagram protocol, or UDP packets, and then send that over the network. Dual stack is another transitional technology used in our routers, and this allows network administrators to configure their devices to support both IPv4 and IPv6 simultaneously. This effectively creates two native networks, but only uses a single layer of hardware devices. It's called dual stack because we're running two stacks or variants of IP addressing on a single piece of technology. GRE tunnels, or generic routing encapsulation tunnels, are going to be used to carry IPv6 packets across an IPv4 network by encapsulating them inside of a GRE IPv4 packet. This effectively creates an IPv6 tunnel inside of an IPv4 network, but it does require an explicit tunnel to be created first, unlike the 6-to-4 solution that I mentioned earlier. Now, why would we want to move away from our standard IPv4 networks anyway, though, and move into IPv6? Well, there's a couple of reasons for this shift. The first reason is that we need a larger address space because the IPv4 started running out of space, even though there was 4 billion public IP addresses. And this simply isn't enough for the current needs of all the varying networks deployed across the globe. Now 4 billion IPs sounds like a lot, but we start figuring out all the laptops, desktops, cell phones, servers, TVs, refrigerators, and other smart devices out there. It really isn't enough in our modern world. I mean, just at my house I have at least 20 to 30 devices, and I'm just one person with billions of people on the planet. There's simply enough public IPs to go around. If everybody has one with only 4 billion IPs. So IPv6, on the other hand, gives us a lot more space inside the public addressing area. IPv6, on the other hand, provides us with 2 to the 128th IPs, ensuring that we won't run out anytime soon. That number is 340 with 36 zeros after it. This is enough IP addresses for every man, woman, and child on the planet, with plenty left over to spare. Now, another reason to transition to IPv6 is that it provides increased security by incorporating IPsec into the protocol itself by default. Now, IPv6 header has also been simplified, and this increases the performance of IPv6 networks over a standard IPv4 network. Finally, IPv6 provides the stateless auto-configuration of devices on your networks. Each device can create their own IPv6 address as either a link local or global unicast address without the need for an in-depth configuration. This again simplifies the creation of networks and the ability to route traffic across wide area networks. All in all, we're going to continue to see a large migration from IPv4 into IPv6. So we definitely need to consider how to best support IPv6 as we begin to construct our organization's networks. Thank you for joining us in exploring these fantastic router features. We hope these tips help you make the most of your internet experience at home and beyond. Don't forget to like this video if it was helpful and subscribe for more tech-focused content like this one. Until next time.